Hey everybody, this is a response to TyYann's most recent puzzle, which is about a man who's on a boat dropping an anchor. And if you haven't seen it yet, you should click right here. And it's a pretty interesting puzzle. It's about a man who's on a boat in a pond, and he drops his anchor, and the question is, does the water in the pond raise or lower when he drops the anchor? And obviously it's going to be a very small amount, but that's the puzzle. And I think a lot of people are getting it conceptually, but lately I've been trying to learn how to do mathematical proofs, and I'm in engineering, and this is kind of a physics engineering type deal, so I thought I'd go ahead and prove it mathematically and show it to you on this video, so maybe you can kind of see the mechanics of how to prove it. So here's my proof. Alright, so we'll start by compiling some formulas, and basically it's just two formulas of force that we need. The first formula we need is just the formula due to the buoyancy of an object, which states that force buoyancy equals the density, that's what that rho is, density of water times the volume of the water displaced, so volume displaced water, times g, which is acceleration due to gravity. And the second formula we need is just force due to gravity on an object, so basically F equals ma, or force gravity equals mass times gravity. So when we start off looking at situation 1, we see we've got our little man in a boat, and I guess that's our seagull anchor. TyYann, maybe you can explain that one. And so we'll write down our first two formulas. Force buoyancy equals that. For our second formula, we'll use force gravity equals mb plus ma times g, and that stands for the mass of the boat plus the mass of the anchor, because they're together. And we know the sum of these forces has to be 0, and so basically force buoyancy has to equal the force of gravity. So we'll write those two out and set them equal to each other, and basically just solve for the volume of displaced water, because that's what we're looking for. And now we look at situation 2, which is when the anchor has dropped. There's a little seagull down there. Anyway, so we write out our two formulas again, but this time the mass of the anchor is not included in Fg. So again, sum of the forces has to be the same. We write them out, and we get that the volume of displaced water looks very similar, but we're not done yet. There's a little bit more water that's displaced just from the volume of the anchor being inside the water now. So we just add that on, and we're good. So now let's compare the two. We've got situation 1 and situation 2, and both of them we're trying to look at the volume of displaced water. And so we'll break those down into what we solved for in our previous equations. And you can't really see which one's greater right now. And so to make it look more apples to apples, we'll multiply our VA over there by rho water over rho water, which is just 1, but it makes our equation look much nicer. And so now we can cancel out rho water on the bottom of both, and we can also cancel out the mass of the boat on both sides. And so now we just have the mass of the anchor on one side and the volume of the anchor times the density of water on the other side. It's still kind of hard to see which side is greater, and so let's use the basic definition. Density is mass per volume, or in other words, mass is volume times density. So we'll take our mass of our anchor there and replace it with volume of the anchor times rho of the anchor, which is the density. And so now we see that the volume of the anchor is on both sides, so we can cancel that out, and all we have left to compare is the density of the anchor versus density of the water. And we know that the anchor is more dense because it sinks in the water. And so since the left side of this is greater than the right side, that means that situation 1 displaces more water volume than situation 2. And so when the anchor is dropped, it now displaces less volume, and therefore the water level drops. And so that's the proof. If you see any errors in my logic, or if you have any questions or anything, just leave them in the comments. Otherwise, thanks TyYann for the puzzle, and thanks everybody else for watching.